God, the music faded out. I guess that means I have to do stuff. I have to entertain you now. Hold on, I need a photo, everyone. Thank you. Okay, I can do this. So every time I give presentations, I get extremely nervous, and when I get nervous, I keep adding slides to my deck. So I'm up to 217 slides, which gives me about 11 seconds per slide, so I think I'm actually over time right now. But first off, I want to tell you that I am right, and I will tell you how I know that I am right. It is because I have the microphone and you do not. So there is an easy way for you to tell whether or not you're right. And this talk I wanted to keep in theme with the rest of the keynotes. Well, I'm not a keynote, but I want to keep in theme with the keynotes, and this talk is about death. Actually, it's not. Okay. What I really want to say is that we need a lettuce emoji, and the reason we need a lettuce emoji is so that I can type lettuce pair program. Now I have to do salad pair program, and people just say that doesn't make any sense. Anyway, I really love pairing. I think that I go particularly well with a nice Merlot. Okay, so we're going to talk about exploring memory in Ruby, building a compacting garbage collector. My name is Patterson. I go by the name of Tenderlove on the internet. You may not recognize me in person. You might actually recognize my icon, which is this. I'm on the Ruby core team and the Rails core team, and I like to talk about Ruby stuff or Rails stuff, so if you want to talk about those things, please come say hi to me. I work for a small startup company called GitHub. We're an online code hosting website. But really, our mission is to make collaboration easier. Anyway, I use Git at work. I like Git a lot, and I really enjoy using Git, but I do not want to force push it on you. Yes, 11 seconds per slide. So I wanted to say that we're hiring, and normally, like, I don't like to put up slides like this because we're always hiring. And if we're always hiring, does that mean that we're actually hiring? No. Yes, we are actually hiring. We're hiring, but the important thing about this position is this is an extremely, extremely special, very, very special position. This position is to be my boss. This is not a joke. This is not a joke. Please write down that URL or type it into your computer. I'll wait. I was going to pause longer and have you fill out the application now, but 11 seconds. So, so I have two cats that help me write code. This is Gorbachev, Puff Puff, Thunderhorse. This is my other cat, SeaTac Airport, Facebook, YouTube, Instagram, Snapchat. So please come say hello to me. I have stickers of my cat. If you don't know what to say to me, ask me for a sticker of my cat. I will give you a sticker of my cat. And I want to say thank you to all of you for being here. And I couldn't be here without you. And I sincerely mean that. And I mean that in two senses. One, I'm glad that you're here at my talk. So you came to see me, and that is good. And the other sense is that I don't think that Ruby could be here without you. And I don't mean that in the like, oh, we're all Ruby programmers way, like, great, you're a Ruby programmer. I mean this in a much more concrete way, and I actually mean that. So I mean that in terms of actual funding of Ruby development. And I want to call out, I was inspired by Shibata-san's talk yesterday. I wanted to call out some of the hidden sponsors of Ruby development. I want to take a second to do this, because I don't think that they get enough praise or publicity in our community. And I'm going to contrast this with people who are not hidden sponsors of Ruby development. For example, all of these companies. GitHub sponsors me, Heroku of course sponsors Mats and other core team members. All of these companies sponsor people who work on Ruby or Rails, and they directly sponsor these people. And I think these are the companies we think about when we think about sponsorship of developers. Now, in my opinion, I feel that these large sponsors of open source development make us feel guilty, because we think to ourselves, well, you know, what am I doing? What am I doing for Ruby? Or what is my company doing for Ruby? And I think that this guilt feeling is kind of dangerous, because we get into this cycle of feeling bad. We feel bad about ourselves, and I want to introduce the hidden sponsors of Ruby so that you don't feel so bad about yourself. And the way I want to show this is I'm going to describe the way that we're actually sponsoring Ruby, really. There's a company, Ruby Central controls rubygems.org. They pay for all of the hosting costs of rubygems.org. So this is how all of your gems get funded and are put online. Now, how does Ruby Central get money? The way that Ruby Central gets money is they put on conferences like RubyConf and RailsConf. This is how they actually get funding. And the way that these conferences get money is by you coming to these conferences and paying for these conferences. So I want to do something that Matsuda-san does at RubyKaigi, which is at the end of every conference, he asks everybody, okay, how many of you are here on your company's dime? Raise your hand. That is a lot of you. That is great. So your company is actually sponsoring Ruby development and infrastructure directly. By you being here and learning from us today, you're actually sponsoring Ruby development. So I want to give everyone clap for your company. You should say thank you to your boss, tweet about it online, you know, get some sponsorship going for your company. So if you ever want to say, you know, think to yourself, how can I help Ruby? The easiest way to do that is to be here. Be here, write Ruby, tell your friends, don't feel guilty. You are the hidden sponsors of Ruby development, and I sincerely want to thank all of you for being here. So now let's talk about some technical stuff. I want to talk to you today about a mark and compact garbage collector, and we're going to talk about, oh, I'm sorry, we're getting into some deep shit now. So we're going to talk about a mark and compact garbage collector, and I've been working on GC at GitHub for a while, and one thing I want to focus on is improving copy on write performance with Ruby itself. So we're going to look at memory in Ruby, and I hope I can get through all these slides because I have a nice treat for you at the end, which is a lightning talk that I could not give at the lightning talks yesterday. So I really want to get to that. So let's do this. So we're going to look at 3 different topics. We're going to look at copy on write, what exactly that is. We're going to talk about building a compacting garbage collector in MRI, and then we're going to talk about memory inspection tools. And this is a pretty low-level talk, and I realize that, and I noticed that we have a lot of new people in the audience today, so I wanted to call out some specific things for new people to learn in this presentation. So new people, I want you to focus on things like, you know, what is copy on write? What is compaction? You don't need to know specifically how all of these things work. I just want you to keep them in the back of your head so that one day when you hear these terms or you come across problems, you say, ah, I've heard about this. I know keywords that I can Google and look up later, because I know that any of you in the audience can do all of the stuff that is in my presentation today. It just might take some Googling around. I'm not supposed to use Google as a verb, I heard. But I did. Sorry, Google friends. So experienced people, if you already know what these particular terms mean, I want you to look at the algorithms and implementation details that I'm going to talk about today. So first, let's talk about copy on write optimizations, or as we shorten it to COW, which I always think about a cow whenever we talk about this. So what is copy on write? Very simply, it means that we don't copy something until we write to it. And I'm going to show you an example here in Ruby. So here's an example of copy and write optimizations with Ruby strings. So first off, we allocate an initial string, and if we look at the size of that string, we'll see it's a little bit over 9,000. Thank you. 11 seconds. Okay. If we duplicate the string and we look at the size of it, you'll see that the size is actually 40, and that's because the memory was not actually copied. That string wasn't copied. But after we write to the string, you can see that the size of that second string is actually now over 9,000 as well. So we copied that string on write. Now we also do the same thing with arrays. You can see this with arrays. Unfortunately, we don't do this with hashes. Maybe we can fix this. I'm not sure why it's implemented this way, but this is the way it works today. So the reason that we can get away with this particular optimization is because when we duplicate something, if we copy something, there is no observable difference between the copy and the original. Since there's no observable difference, we don't actually need to copy it until there is some kind of difference. So this optimization isn't just limited to Ruby programs like I demonstrated. It's also, we can use this optimization in many places, and one of the places that this is used a lot is inside your operating system. The operating system takes advantage of this when you create multiple processes, and that happens when you use the fork system call. So if we use fork in Ruby, we allocate, in this program, we're allocating a very large string. Then we create a new process by calling the fork method. The fork method copies the current process to the child process, just like we did when we called dupe on a string. But since nothing has changed between the parent and the child process, it doesn't actually copy anything. However, when we write to the string, the operating system copies the memory that changed to that child process. So we're copied on write. Now, if we imagine this string laid out in the operating system's memory, it might look something like this, where we have a parent process with this large string spread across many pages. Now, each of these pages is about 4K, but I guess it depends on your operating system. After your program forks, the child process will create a bunch of pages that point back to the parent process. And when the child process writes to part of the memory, only that page that got written to is actually copied. So it doesn't copy the entire thing, it only copies one particular page. Now, whenever this happens, this is called copy on write page fault. And we can use operating system instrumentations to find these and measure them. In general, in order to increase copy on write performance, we want to decrease the number of page faults that we see. So why is copy on write important to us? The reason it's important to us at GitHub is because we use a forking web server. This means it creates a parent process. Our web server creates a parent process with many children, and the setup looks a little bit like this. All the children handle the web requests that come in. These children were forked off from the parent process. So a problem is if each child process loads a copy of Rails, then we end up with 3 copies of Rails in memory. Now, unfortunately, this uses a lot of memory. Also, it means that we have to spend the time loading Rails into each one of the child processes. If we change this such that we load Rails in the parent process and then have all of the children fork after that, all of these child processes will point back to the parent's copy of Rails. So this actually reduces our boot time because we only load Rails once, and it decreases our memory usage because we only have 1 copy of Rails in memory at a time. Now, this is actually how it works today. So if you're using Unicorn in production, this is the way it is working. But this isn't actually the type of optimization that I'm interested in. I'm interested in reducing page faults. And as I said, page faults happen when something writes to a shared page, to a page of memory that we're sharing between processes. Now, what causes page faults? The thing that causes page faults is mutating shared memory. And what mutates shared memory? Well, the garbage collector mutates shared memory. So what things does the garbage collector do to mutate shared memory? It used to be in the past that during the mark phase of our process, the mark function would actually go through and cause your entire program to get copied into the child process. So what would happen is we would have, say, a parent process with some objects in memory, a child process pointing at all of these, and during the mark phase, the garbage collector would actually go through and write a flag on each object as it was marking it. And once it wrote that bit, the object would get copied to the child process, and we'd end up with all objects being copied between all processes. Now, unfortunately, this is a bit worse than it looks because, as I said, the operating system copies 1 page, which means that rather than copying 1 object at a time, if we happen to mark one object in the child process, it might actually copy the entire page, whether or not there's an object in that slot or not. So we could end up with many objects being copied. Now this was solved with a technique called bitmap marking, and this was fixed a long time ago, so you don't need to worry about this today. The way that bitmap marking works is instead of storing that mark bit on each object, it actually stores those mark bits in a table off to the side. So this table does get copied between processes, but this table is much smaller than all of the objects in memory, so you only have a small amount of memory that is copied between processes. Now, another thing that the garbage collector does that is unhandy is object generation. So Ruby has a generational garbage collector, which means that as objects get older, they age, and we keep track of the generation that they're in. Every time an object survives a garbage collector, its age increases, and the maximum, the oldest an object can get is 3 GCs old, if I remember correctly. And we have to store that age somewhere, and the place that we store that age is actually on the object itself. So this results in a similar problem to the mark bit, in that every time we do a garbage collection, if we have to increase the age of the object, that object gets written to, and then it is copied to the child process. So there's a workaround for this, which is in a gem called Nakayoshi fork. If you use a forking web server in production like we do, you should check out this gem. Now, the gem works on the following principles in that generations are bounded. When an object reaches age 3, it does not go over age 3, it stays at age 3. Now, the other principle is that objects created before you call fork are going to get old. We assume that they will get old. So if we work with those two assumptions, the solution for this problem is we just GC a few times before we fork. So if you take a look at the Nakayoshi fork source, that's essentially what happens. We just GC a few times and then we call fork. So you can use this gem in production today if you're using a similar setup to us. The other place where the garbage collector will write to memory is during object allocation. Now, this one is kind of surprising, but just allocating an object can cause memory to be copied from one process to another. So, for example, we have two processes, parent process and a child process. The child process allocates a new object, for example. The problem is that a Ruby object is, of course, smaller than one system page, and since we wrote to that page, the operating system will actually copy the entire page, not just that one object. So the effect is that we have pages that have space in them, but those pages will be duplicated between processes. So how do we fix this problem? Well, we reduce the space. And how do we reduce this space? We do that through a technique called GC compaction. So what this looks like is before we fork, in this case we have a process with 2 pages, if we fork the process, both pages have potential to be copied to the child process. But if we move some of those objects around, now only one of those pages can possibly be copied to the child process. So we have a child process pointing at both, and when we go to allocate an object, only one of those pages has free space in it, so only that page will get copied to the child process. So now let's take a look at GC compaction. What is compaction? Well, it's very simple. All it is moving these objects around until there's no space left. We have all the space grouped in one place and the objects grouped in another, and hopefully after moving all these objects around, your program will continue to work. That was my goal, anyway. So why should we compact? Well, for me, there are 2 important reasons to implementing this. One is to reduce memory usage, as we talked about. And the other reason is because somebody told me that this was impossible to do. Last year, at RubyConf last year, I presented a garbage collection technique where we took objects and depending on the type of the object, we would allocate them into different heaps because we knew that some were going to live longer than others. And I presented this technique last year because I had made the assumption that moving objects was impossible. In fact, I actually said that in my talk, where this technique is impossible to do. And after that talk, Koichi came up to me. Koichi is a VM author. He came up to me afterwards and he said, "Aaron, why do you say that this is impossible to do?" And I said to him, "Well, because other people told me it's impossible to do." And he said, "Well, have you tried it?" I said, "No." And he said, well, maybe you should try it before you think it's impossible. And I'm like, you know what? That's a really good point. So I had to try it, and it turns out that it is actually not impossible to do. So let's talk a bit about compaction algorithms. I'm going to talk about a compaction algorithm called two-finger compaction. This is the algorithm that I chose to implement in the garbage collector, and I'm going to go over the disadvantages of this algorithm first. The disadvantages of this algorithm are, well, it is slow, and it moves objects to random places throughout memory. And this second statement is a little bit more nuanced than I have time to go into today, so if you want to know more, come talk to me. But these two disadvantages are actually pretty bad. We don't want a slow compactor, and we don't want to move objects to random locations. It's not really great. But this algorithm has one extremely good advantage for me, and the advantage is that it is easy. This is why I chose this algorithm. It is easy to understand, and it is easy to implement. So the algorithm, in general, garbage compaction algorithms go something like this. We move a bunch of objects around, and then we update all the references of those objects. So object movement looks a bit like this. So imagine that we have a heap layout like this. You have a bunch of objects in memory that look like this, with some free space in between. Each object is fixed width. Each object has its own address, and you can see the addresses along the top. So each location in memory can either be empty or it can have an object there. Now, two-finger compaction works by placing essentially two pointers at either end of the heap. These are, we call them fingers. One is the free pointer, one is a scan pointer. The free pointer moves to the right until it finds a free space. The scan pointer moves to the left until it finds a filled space, and then those two spaces are swapped. So in this case, we don't have to move because the free pointer is already at a free location and the scan pointer is already at a filled location. So we actually just swap those two. After we swap those, then we leave a forwarding address in the place where the object used to be. So we say, okay, this object used to be in B. It is now in 1, so we're going to write a 1 to that slot. Now, we continue on with the algorithm, moving the free pointer until we find a free location, moving the scan pointer until we find a filled location, swapping that, and leaving a forwarding address. And we keep repeating this process until the two fingers meet. God, this is way longer than 11 seconds. So once the two fingers have met, we're done with the compaction part of the process. Now imagine that our heap layout looked a little bit like this, where we have a hash. This hash may reference a symbol and a string. The hash is in a certain location. The symbol and the string are in other locations. Now this is before compaction. After we do compaction, the heap looks like this, where the string and the symbol have moved, but they're in a different location, and now the hash is pointing at two locations where there is no string or symbol. In order to fix this, we have to update the references for each object. So the way that we do that is very simply, we start at the beginning of the heap. We look at the object, see, does this object have any references? If so, we find those references and then update them. So none of these have references until we get to 4. 4 has references to 6 and 7, but those go back to 5 and 3. So we update those to point at 5 and 3, and then we continue on until we finish scanning the heap, updating all of those references. Yay, we did it. Then we change all of those forwarding addresses back to free spaces, and we're done. We have our heap compacted, and we can continue on with our program. So let's take a look at some of the implementation details. You can find all this code. It is open source at this fork on GitHub, the company where I work. I need a manager. So this fork introduces a new method called gc.compact. It allows you to manually compact your heap. The way that we've used this is this is just some pseudocode. Essentially, what we do is we load all of Rails and its dependencies. We load everything in our application, any type of startup stuff that we need to do, and then we compact everything that's in memory, and then we fork off all of our child processes. So I don't know why I put arrows there, because I just told you all that stuff. We compact it and then move on. So let's take a look at the actual changes that I had to make Most of the changes I had to make to Ruby in order to implement this are in gc.c, and that is because that is where the garbage collector is. So I'm going to talk about some of the biggest changes I had to make. I had to introduce a new function called gc.move, or gcmove. All this function does is swap two locations, like this. Now, I had to introduce a new type of object called a tMoved object, and this tMoved object indicates that that particular location is a forwarding address. So this particular location is a tMoved location. So that's a way for me to tell, oh, this isn't actually a free space, this is a forwarding address, and I need to update references here. I've introduced a new function called gcCompactHeap. All it does is move those two pointers together. Then I introduced a function called gcUpdateObjectReferences. All this function does is update references like that, fixes them, which I messed up the numbers, but you get the idea. Now, what's interesting about this function is this is the most difficult function in the implementation, and the reason this is the most difficult is because it has to update all of the references. It has to know how to update references for every type of object that's in your system today. So if you take a look at this function, it's essentially a giant switch statement looking at the type of object that it needs to update. And it'll actually call out to different helper functions. For example, we have one for updating arrays, one for updating objects, one for updating hashes, method entries, et cetera, et cetera. Another thing that I had to introduce is a table called a pinbits table. And now, up until now, our discussion has been that every single object in the system can move, and unfortunately, this is not true. So I want to go over what objects can move and what objects can't move. So until now, we've said that all objects can move. Every object can move in the system. This is great. Now, unfortunately, we have to do a thing called finding references, where we have to find references to objects and then update those references. So how do we find those? Now, if we have the case of a pure Ruby object, it's very easy because we have, let's say in this example, we have an instance of foo pointing at an instance of bar, and that's stored in an instance variable called bar. Both of these objects are pure Ruby objects. Because they're pure Ruby objects, the GC knows the internal implementation details of these objects. So if that thing ever moves, it's fine, we can update it. Now, let's say we have a foo class and a bar class, and the foo class is implemented in C, and the bar class is implemented in Ruby. Well, how does our garbage collector find this reference to update? If we don't update that reference, then this program could crash. So the way that we do this is, for example, we have this exact same setup here. If the GC moves bar, it'll crash. So we don't want to do that. This is a bad thing. So the way that we deal with this is every time every time a C object references a Ruby object, it actually has to call RBGC mark on that object to prevent it from moving. So the technique that I chose to use was let's say we have a C object that points at a Ruby object. We need to know that this reference cannot move. So when RBGC mark gets called on the object, we say, oh, hey, we can't actually move this object. We have to store that somewhere. We say, well, you called this mark function. We cannot move that object because you're a C object referencing a Ruby object. We have to store that someplace, and that is the pinbits table. So everything that can move, actually, I changed the RBGC mark function to do two things, which is mark the object, then pin the object in the pinbits table. So our GC compaction algorithm actually is do a full GC, compact all the objects, and then update the references. So doing a full GC fills our pinbits table so we know what references can't be updated. So far, what can move? Everything except objects marked with RBGC mark. Okay, good. Now we have some movement problems. Everything was easy. Everything about compaction was easy, I thought, until I had to implement it. I feel this is all of programming. So I want to talk about some problems I had while implementing this compaction. First off is hash tables. We're going to talk a little bit about hash tables. So when we have a hash table, I assume most of us know how our hash tables work. We have to calculate a key for an object, and we put that object into the hash table using the key. So the default key is actually the memory address of the object. So if we ask for the hash key on a Ruby object, it's actually the location in memory where that object is. So because that hash key is the location, it means that if we move the object, well, the hash key changes. And unfortunately, that means you wouldn't be able to look up your objects in the hash anymore if we didn't update that. So the fix for this is to cache the hash key if it's ever calculated on the object, but I haven't implemented this yet. So it's just not done. But because of this, we can't move objects that are used as hash keys. So what can move? Everything except objects marked with RBGC mark and hash keys. So another problem I encountered was dual references. Oh my God, only 10 minutes, let's move. So in this case, we have a C object pointing at a Ruby object and a Ruby object pointing at another Ruby object. And the author said, well, the author of the C extension said, I know that the Ruby objects won't move and that this Ruby object has a reference to another Ruby object. So I'm not going to call RBGC mark with the C object. And unfortunately, what that means is this bar object can move, and we end up with a T-moved pointer in this particular location. And maybe the compactor will update this. It'll update the pure Ruby implementation, but it won't update the C implementation. So our program crashes. In this particular case, we fix the code to call RBGC mark or use only Ruby, and you can see an example of this in the message pack gem, which I sent a pull request there. So what can move? Everything except objects marked with RBGC mark and hash keys and dual references. The next problem is global variables. So global variables in C, we have a global variable that's referencing a Ruby object. The GC does not know how to update global variables in C. So in this particular case, I changed this to use heuristics to pin those objects. We know that C extension authors only call these certain functions to generate objects, so those certain functions will pin their objects. So for example, RB-defined class will pin objects. So what can move? Everything except objects marked with RBGC mark and hash keys and dual references, and objects created with RB-defined class. So our next problem was string literals. So this is a string literal. Now what happens when Ruby compiles your code, it turns it into instruction sequences. While these instruction sequences are made, they turn literals into objects and then store those objects in an array. It also creates bytecode, which is a binary representation of your program, and the bytecode points at an address of the literal. So if the literal moves, then the bytecode needs to be updated as well. Now unfortunately, this is actually very hard. So this is just hard. Updating bytecode is hard. It is possible. I just have not done it yet. But this practically means that literals cannot move. So what can move? Everything except objects marked with RBGC mark and hash keys and dual reference objects and objects created with RB-defined class and string literals. It seems like nothing can move, right? But I have some good news about this. And the good news is that, well, most of these cases that I presented to you today where objects cannot move are things that we can fix. The only one that we really cannot fix is this RBGC mark case that I showed at the beginning. All other cases can be fixed. And even with these restrictions put on our program, in a Rails application, 46% of the objects in memory can actually move. So this is what our heap looks like before we compact. Red are objects that cannot move, green are objects that can, white is free space. After compaction, this is what our objects look like when they're moved together. So let's look at inspecting memory, and I gotta go through this very quickly because I really wanna show you my lightning talk. Well, I'm sure we all care about the lightning talk more than inspecting memory, honestly. So this is my favorite way. This is my favorite way to inspect memory. This is object space dump all. You should take a look at this. It dumps all of your memory. This is the easiest way and fastest way to understand the way your Ruby program uses memory. You can use this function to dump all of your heap into a JSON file. Use it like this. We can use this to measure Rails boot. So this particular example shows the way that I measure the Rails boot, the boot process using compaction. So we'll require object space, compact the heap, and then dump all the objects out. The output of this, if you look at the JSON file, there's different lines that look one line per object. and one object is just a hash, JSON hash of the object. Now, I've prettied up the output a little bit like this. What's cool about this is we can see the address of the object. This is the address in memory. We can also see all the addresses that it references, as well as the size. Now, what's neat is this address is actually the location in memory, and this is important to me as a GC developer because it means that when objects move, I need to understand their locations. Now, what's also cool about this is if you understand the format of these addresses, you can actually make a graph of what objects look like in memory. So if you dump the heap, you can actually generate a graph that looks something like this, where we've calculated where the objects are and where the free space is between all of these. So this is a graph of the heap for Rails 4.2. This is what the heap looks like before we compact. This is after compaction. And we can also see many of the objects were moved to fill in blank spots. So here's another example. This is the same graph. However, the green objects are objects that can move. Red objects are objects that cannot move. We can see before and after heap compaction. If you go to this URL on github.com, I need a manager. You can use this code to generate your graphs. We can also inspect copy and write memory, but honestly, I only have 4 minutes left, and I really, really, really want to show you this. I really want to show you this, lightning talk. So you should go look at proc file system. It has awesome information, including address ranges, which calculate RSS and PSS of your program. These are neat numbers. TLDR, use PSS instead of RSS when you're using forking programs like Unicorn. Yes, I don't care. Let's go to my thing. I don't care. Okay, so, all right. Actually, these are sad numbers. So unfortunately, let's look at the sad numbers and then go to the lightning talk. Okay. Unfortunately, after we calculate the savings, we use PSS to calculate the savings of GC compaction. Unfortunately, after this, we only see about 150K of savings. But this is on a small program. This isn't on the scale of this isn't our entire application at GitHub. So I still need to run it against our complete app at work. Conclusion is compaction savings are unknown, but this is because we've only tested on a test program and because of the caveat of so many objects that cannot move. Use object space, check out this proc file system. This is only on Linux. Again, why compact? I want to end this. Why compact? For me, the reason was because I thought it was impossible. And I learned something. I learned that it is possible, and that I should be questioning my assumptions about these things when I think that they're impossible. Because with computers, it turns out that most things actually are possible. We just have to try harder. Specifically, I have to try harder. So thank you. Thank you. Let's clap now. Okay. Okay. 2 minutes. All right. Thank you. 2 minutes. My lightning talk. Okay. Yes! Yes! I am going to talk to you about how I became extremely famous in Japan for one day. I made a tweet that had one character in it. One character, and it got 53,000 retweets and 83,000 likes. And I want to talk to you about how this happened. So, the way I'm going to talk to you about how this happened is, first off, I want to tell you that I love Japanese. I think that Japanese is a very interesting language to study. I've been studying Japanese for over 10 years now, and I'll tell you the way that I got started studying Japanese is because back then, actually, this is my 11th RubyConf, which is crazy. I can't believe it. Back then, when you Googled for stuff in Ruby, many blog posts came up in Japanese. And I could read the code, but I could not read the contents of the blog posts. So I really wanted to know what they were saying, and this is what got me started. Now, the great news is that 10 years later, I can finally read those blog posts. I just don't need them. Anyway, so I want to share some things about 45 seconds. We're fine. All right, so I want to share some things about Japanese language first. So there are three writing systems: kanji, hiragana, and katakana. There's also a fourth writing system called romaji, and this one is this one is used typically to teach Japanese to Westerners. Sometimes you'll see it in other writing, but it isn't as common as the previous two. A handy thing is that katakana is typically used for imported words, so borrow words, so you're able to tell the difference between something that's a Japanese word and something that's been pulled in from another culture, so you can tell those apart. The language is phonetic. Each character has one pronunciation. It's actually called the goju-on for 50 sounds. Unfortunately, there are only 46 characters. I don't understand why there are 50 sounds and only 46 characters. I think it should be called 46 sounds, but I'm not an expert. So if we look at pronunciation, all of these are pronounced the same way. Every one of these things has the same pronunciation, which is kanji. It reads kanji. The problem is that the very last three, the meaning is ambiguous. So these last three, if you were just to read them, you wouldn't know what they actually mean because there are multiple words that are pronounced the same way, where the Chinese characters at the top are specific, so you know what it means. Now, a thing that I really like about Japanese, in contrast to languages like German, is that Japanese sounds are a subset of English sounds, which means that as an English speaker, I can mostly pronounce everything in Japanese, where I cannot pronounce anything in German. So Japanese came from China. The origin of these Chinese characters is a script called bone script. These were scrawled on bones and turtle shells. They were just pictographs. These pictographs later got turned into characters. These characters were taken from, in the early days, Japan did not have a writing system, so they had people come from China. They imported the writing system from China. Yes. Yes, no one knows why. All the Japanese people, okay. So they imported all the Chinese characters from China and then actually derived hiragana and katakana from these Chinese characters. So the cool thing is that kanji are pictures of stuff. This contrasts to Roman characters, our language, where it's not pictures of stuff. So let's go on to why I got famous for a day. This verb is to laugh. It means warao. The pronunciation is warao. It means to laugh. Now, this was shortened online from warao to just the character warao, so this is just the picture. Now, people didn't want to type out the whole thing, so they shortened the character to just W. So you can type W a whole bunch, and this just means this means to laugh a lot. So WWW is essentially LOL. Now, what's really interesting about this is that eventually people started seeing www as a picture. So it actually became a picture, and people started thinking that it looked like grass. So if you imagine all these W's, they look like grass growing. So then this got converted into this character, which also means grass. So what I think is so interesting about this is that we started out with essentially a picture. We got the laugh picture. We turned that into a non-picture. We don't see these, us Westerners, we don't see these as pictures. So it got turned into a non-picture, but then was seen again as a picture of grass growing. And then that got turned into another picture again of actual grass. So through this convoluted series of events, grass became LOL. Now there's different forms of this. Kusahairu means grass grows or LOLing, and then we have another one that's daisogen, which is like a huge field of grass, which means like really laugh. So I found this like completely fascinating. Once I learned this internet slang, just from my perspective studying this language, I thought it was so neat. So I explained it online, thinking, everybody's gonna find this interesting. So I made a bunch of tweets about how I thought this was interesting. Then somebody took screenshots of it. These are the screenshots, and tweeted, "Oh, this foreigner is seriously explaining kusahairu." So I just, and then, so my mention just started blowing up. It was so much, my watch crashed. I could not use my watch. I was famous among normal people. I actually happened to be in Tokyo at the time when I was doing this. And I was going around with Justin. We went into a bar, and Justin pulls out, of course, he pulls out his phone, and I'm at like 40,000 retweets at this point, and shows it to the bartender and says, "Hey, do you use Twitter?" The bartender says yes, and he shows it to her. Have you seen this? Have you seen this tweet? Yes, I've seen this tweet. It's him. This is a true story. So I want to say to all of you, don't use this. It's not proper Japanese. You should learn correct Japanese. Do not use this. Also, a very interesting thing is it actually means the F word in Chinese. So two completely different meanings. And to find out why this is, look up on Wikipedia, grass, mud, horse. And it's on Wikipedia, but the meaning is extremely offensive. But what I think is really neat about this, you should go look this up. What's neat about this is that it's a phrase in China, used in China to subvert internet censorship, which I think it's actually a pun used to subvert internet censorship, which I think is amazing. So, in conclusion, foreign languages are awesome. I recommend Japanese. If you want to start studying it, this is a good book. Thank you.